Hello, welcome to another Further Maths tutorial video where today we're looking at how to solve inequalities involving rational functions. In layman's terms, a rational function is here being defined as an algebra fraction being made up of polynomials in the numerator and the denominator. Now it's worth noting that there are two main methods for solving these sort of inequalities in the most efficient ways. And we're only going to be covering one of those two main methods in today's video, and in a separate video we'll be covering that other method. If you're familiar with inequalities from before in Maths A level, particularly solving quadratic inequalities for instance, you're probably already aware that doing a bit of algebra and graph sketching are together the two main parts of solving inequalities, and that's still going to be the case for both the methods we're going to be looking at, but out of the two methods in comparison to each other, the method we're looking at today is slightly easier on the algebra side of things, and then slightly more time consuming when it comes to drawing the graph, whereas the other method in the other video will be slightly more time consuming on the algebra side of things, but slightly easier on the graph side of things. So it very much comes down to a choice over which one you prefer to use. But I would recommend you make sure you're familiar with both of the methods, even if most of the time you're just picking one of them and just using that one method out of the two methods that you prefer. But what do we need to know in order to be able to do today's method? Well, I've kind of already given the game away because one of the main things is you need to be able to know how to solve quadratic inequalities, because basically the method we're looking at today is just an adjustment to that main method you've already come across before. Basically the two stages of finding critical values, which is where you effectively treat the inequality like an equation to find the boundary values that solve the inequality, and then do something afterwards, which is drawing a graph to then help you find out what happens to the inequality signs in relation to those numbers. However, there is one extra adjustment we have to make to that very basic method, which is that there are additional critical values that need to be found because they're caused by any points on the graphs where discontinuities happen. The most common example of discontinuities that you have to deal with in Maths and Further Maths A level is vertical asymptotes. So the x values at which vertical asymptotes occur, those x values will be extra critical values to be included as part of your solution. A quick way of finding vertical asymptotes would be to just set the denominator of the algebra fraction equal to 0. That's a nice cheaty quick way of being able to find vertical asymptotes for rational functions. So there we go, it's a nice way of being able to quickly find that stuff. It's also worth noting that critical values caused by these asymptotes do have to be treated slightly different to the other critical values, which is that when we're writing our final answer, the critical values caused by these vertical asymptotes or discontinuities can't ever have a less than or equal to or a greater or equal to symbol next to them in the solution to the inequality, even if the original question has those inequalities written in it. So that's something to note, and that does mean when identifying them, you do almost have to identify them separately, highlighting them to yourself that they have to be treated differently. The other last thing we're going to have to deal with is basically slightly more complicated graphs. Because the sort of inequalities we're looking at algebraically look more complicated, the graphs are also a bit more complicated, and therefore we need to be able to draw graphs specifically that have horizontal and vertical asymptotes, which is something you've dealt with a bit at Maths A level, but controversially in Further Maths A level, you might also have to be dealing with graphs that have multiple vertical asymptotes, or even graphs that have diagonal asymptotes. Now, at this point, I do have something important to mention to you, which is that exactly how this is approached varies exam board to exam board. For some exam boards, being able to draw these more tricky graphs can just boil down to being allowed to use your graphical calculator to just find out what the graph should look like fully, and then just using that to deduce what happens to the inequality signs. Whereas for some of the exam boards, there's an entire topic focused on knowing how to draw these sorts of graphs manually. I will, in the description to this video, have an up-to-date description making it clear what exam boards you do or don't need to know that information for. And actually, therefore, for today, I'm going to be just treating it as if you can use a graphical calculator to draw these graphs for you if you wish, rather than going into the full drawing them manually sort of thing. It's worth mentioning, just for interest's sake, that graphs have diagonal asymptotes. They're officially called oblique asymptotes. But as I said, if it's not something that's on your exam board, then don't worry about that specifically. We can just use a graphical calculator to help us out. Okay, with all of that out the way, let's get on with an example. Now, it's worth mentioning or reiterating from before, as I said, there's more than one method for going about solving these sort of inequalities, and most of the time you can just choose which one to use. Some people get a bit freaked out with the wording, where because it's saying use algebra, they sort of worry that you're not allowed to be using graphs at all, and that's actually not the case. We are going to be still drawing graph, even though it says this term use algebra, and actually this wording they've used in the question doesn't narrow down which of the two methods you have to use. Both of them do use a bit of algebra and a bit of graph drawing, and all they're saying when they write this sort of wording is they're basically implying you can't just use calculator technology to completely solve this entire inequality for you. You actually are going to have to do some calculations and show those calculations in order to be able to get the marks for this sort of stuff. Cool, right then, so we're solving this inequality. Now therefore the first thing we want to do is find critical values, part of which, from quadratic inequalities, we already know is just treating the inequality like an equation and solving that as an equation. However, something worth noting, there are lots of ways you could approach that, but something I've noticed in a lot of mark schemes, they like to set these questions out in a certain way, and therefore I'd recommend you set out your work in the same way that I am, just because that's a nice safe way of guaranteeing yourself getting the marks, just because if they're always setting them out that way, that shows it's kind of a good way mathematically of approaching this stuff. That's not to say you're guaranteed to lose marks if you don't approach it in this exact same way I've done it, but it's just that it's good advice to do so. So the way they generally seem to like people to lay it out is they like people to start by moving all the algebra onto one side of the inequality sign. This makes sense because it's, mathematically allowable, because of course, regardless of whether there's algebra involved, you're allowed to add or take away whatever you like onto both sides of an inequality sign, because it doesn't matter what number you deal with, that never has an effect on what direction, what way around an inequality sign is. So it's a very definite action you can do, operation you can do, because you know what's going to happen as a result of that operation. The next thing they often like people to do is to basically gather all of the things so they're absorbed into one big fraction, one big algebra fraction for the entire inequality. So therefore that means you're going to be required to make a common denominator. So of course for us, that means we're going to have an easy common denominator of x minus 2, x minus 3, by multiplying the denominators that we can already see together. Of course, be efficient. You don't always just automatically multiply all the denominators together. It's always about picking the most efficient common denominator that you can get. Anyway, therefore that means the first fraction would have had to have been multiplied by x minus 2 in order to create that new common denominator. The algebra fraction of minus 80 over x minus 2 has to be multiplied by x minus 3 to get that common denominator, and the minus 4, which officially has a denominator of 1 at the moment, would therefore have to be multiplied both by the x minus 2 and the x minus 3 to get that required common denominator. There you go. And then, of course, is just a bunch of algebra simplification after that. So bear with me while I now have to do all of this. Some people like to, basically rush through these steps, but that's when they make silly mistakes if they do. So although maybe I'm writing out more than what some students would like to write out when doing this stuff, by taking the time writing this stuff out, it helps me avoid any very silly errors. It means I can feel more confident I'll get all the marks. So for instance, already on the top I can see that 80x and the minus 80x are cancelling out. The minus 160 and 240 become an 80. And then we get a minus 4x squared, a plus 20x, and minus 24, all over that denominator. And then doing some more simplifying, we get a quadratic. And then Something they also generally like to do in the mark schemes is they like people to factorise the numerator as well if it's possible to do so. That's why I didn't bother multiplying the brackets on the denominator, because they like the entire algebra fraction to be fully factorised, just because that's something that's helpful for the next stage we're going to be doing anyway when finding critical values. So fine enough, we can factorise -4 out of that entire thing, and then if you do, that'll leave you with x minus 7x plus 2. In case you're wondering how I spotted that, I noticed that if we divided that entire quadratic by -4, you get an x squared minus 5x minus 14. So that's why I was able to do that by inspection. Of course, you can use quadratic formula to help you know how to factorize it if you prefer. What this is all leading up to, though, is it now enables us to find critical values. It's always a good idea, like we said for quadratic inequalities, to write it almost as a mini title, critical values, to make it very clear, because we're now going to be writing x equals, and we want to make it clear that when we're writing x equals, we're not saying the final answer to the inequality is x equals, because that would be wrong. So we're just making it clear what we're finding when we're writing x equals, making it clear it's not the solution to the inequality as a whole, and that we're aware of that. So the easy way of finding critical values is to basically treat the inequality like an equation, and then therefore solve that equation. In this case, therefore, you multiply both sides by the denominator. That means you just get the quadratic on the top. And then, of course, because we've already factorized it, we can already see the critical values would be x equals 7, x equals -2. However, we are also aware now, as I said earlier, that there are additional critical values caused by discontinuities, places where there's vertical asymptotes. So therefore, we've got some extra critical values to find. So asymptotes occur, if I'm going to write the word occur, when the denominator is equal to 0. So therefore, I'm going to set the denominator equal to 0. And therefore, that's going to get the additional critical values of x equals 2, x equals 3. Those are vertical asymptotes, and they are also critical values. And the reason I've classified them slightly differently is because we're aware, although the original question has a greater or equal to sign in the question, which implies that the answer will have that inequality sign in as well, that's not going to be the case where the critical values of x equals 2 and x equals 3 appear, because it can never equal those x values, because those are parts where the function is undefined. So that's something to be aware of. So we're halfway through the problem. We've found the critical values, in other words, the numbers that will appear in the final answer with inequality signs next to them. We just now need to find out what those inequality signs will be. And to do that, we need to draw a graph. Now, when it comes to drawing the graph, you do have a couple of tactical choices you can really make with this. One of the options is, in the original inequality, you might have some algebra on the right-hand side of the inequality sign, some on the left-hand side of the inequality sign, and you can therefore choose to draw both of those graphs. As soon as you're drawing just one side, you have to draw the other side, so I'm saying you have to draw them both if you're using the inequality written in this form. The reason you might choose to sometimes do that, even though it's requiring you to draw two graphs, is that because the graph has been split up into these two separate graphs, these two graphs are ones that you might individually feel more comfortable sketching without as much, help from graphical calculators, etc., etc. And that is the case here, for instance, because you can look at these two graphs and hopefully recognize they're both transformed versions of the graph y equals 1 over x. So therefore, we don't need quite so much help in order to know what they're going to look like. So let's put that into practice. For instance, 80 over x minus 3, that's 1 over x. Stretch scale factor 80 parallel to the y-axis, and translated 3, 0, positive 3, 0. That means its vertical asymptote is at x equals 3. So putting that into practice, we're going to end up with a graph that looks something like this, and something like this. Poorly drawn, but it doesn't really matter. We're just using this as a tool to help us solve the inequality. We can then also draw the second of the two graphs, and that's again 1 over x with some transformations, more of them this time because it's been stretched, scale factor 80 parallel to the y-axis, translated positive 2, 0, so that means its vertical asymptote is going to be at x equals 2. which we already knew from before, and then also translated 0,4. So it means its horizontal asymptote is now going to be at y equals 4. Cool. And therefore that means we can draw that one as well. And that's going to look something like this, if we get it correct. Something like this. There you go. Cool. So we've drawn both graphs. What this now allows us to do is we can use these graphs to then solve the inequality, because we already can see these two graphs are intersecting in two places, and those correspond to the critical values we'd already found, specifically the ones that weren't caused by the asymptotes. So therefore 7 and -2 are these two values there and there. But then we are also specifically looking for where the graph that's got the vertical asymptote at x equals 3, we're looking for where that graph is above the other one. And so therefore we can see that's this region here that we want, and therefore it's also, what else? It's also this region here that we want. So therefore you can hopefully see very clear that the final answer in theory would be -2 is less than x is less than 2, union with 3 is less than x is less than 7. However, it is a greater or equal to inequality sign, so therefore in the answer we should have a less than or equal to instead of just less than, but only for the critical values not caused by the asymptotes. So therefore we're going to put that less than or equal to next to the -2 and next to the 7, because those are the ordinary critical values, and the ones next to the 2 and the 3 just still have to stay with the less than inequality signs that we've got currently. Cool, so that's one way you can draw the graph to help you solve the inequality. The other way though is to use one of the rearrangements we had. We had already realized that we could rearrange the inequality to get this, which was useful for finding critical values, but also gives you the side option of drawing just one graph, the one that's on the left. Technically you are drawing the graph that's on the right as well, but because we've rearranged to have a 0 on that side, that's just a graph of y equals 0, which is just the x-axis. The advantage of doing it that way is, although you've got a more complicated graph to draw, you've only got one graph to draw, and also you're then just checking whether the graph is above or below the x-axis, which is in some ways easier to tell at a glance. So more difficult to draw, but then easier to interpret in some ways. So that though is where it starts getting into the territory of things you might not be expected to draw by hand depending on what exam board you're doing. Again, look at the description for this video to know whether you need to care about it or not for your exam board. But therefore, if it's one of the ones where you don't need to know how to draw it manually, you can just plug it into a graphical calculator, which will tell you the graph looks something like this. However, you do have to be careful and use your knowledge, basic knowledge of graphs anyway. For instance, we're already aware that this graph has vertical asymptotes at x equals 2 and x equals 3. So that isn't just one single vertical asymptote that's causing that shape we can see there. That's worth being aware of, because actually, again, another reason why you've got to be careful of graphing software is there is a third bit of the graph that you can't see unless you were to really zoom out. Really far down at the bottom of the graph between 2 and 3, there's another bit of the graph that's doing something like that. You can't see it if you were to just sketch the graph unless you zoom really far out, because it is really far down, but therefore that's important to be aware of. It doesn't affect the solution in this case because we're looking where the graph is above the x-axis, because we're looking where it's greater or equal to 0, but still noteworthy. Worth mentioning therefore this time, the critical values we'd found are now, instead of corresponding to points of intersection, well, they sort of are still points of intersection, but they're points of intersection with the x-axis specifically. So that's what that -2 and 7 are corresponding to there. We're looking for where this graph is above the x-axis, so therefore again we can very quickly see we want this bit of the graph and this bit of the graph, and that's why you will end up with the exact same solution we had above, because again you can see that the region we want are in between those two sets of values, and again, once again, we could put the less than or equal to next to the -2 and the 7 because they're just normal critical values, and then the 2 and the 3 just have to have the less than next to them, staying there as a less than, because you can never be equal to them because the graph is undefined, the function is undefined at those two x values. Okay, so this is just one way of doing it. The advantage is the algebra is a bit quicker than the other method, but the graphing is a bit more intense. So it's about whether you like doing that or not. But there you go. Stay tuned for a video on that other method. Do check it out, and I'll see you in a future video. Goodbye.